So, Dolly, oh yeah, Dolly, are you recording?
You're recording, go ahead.
Okay, good. Okay, thank you. Okay, today we are glad to have Dr. Abu Taleb Haddadi from EPRI. So Dr. Haddadi got his PhD from McGill University from Canada in 2015. And then since 2020, he has been with EPRI as a senior technical leader, where he leads R&D activities related to bulk system and distributed renewable energy resources, modeling and system integration impact. He is the chair of SIGRE Working Group C4.60 and also has done a lot of activities in numerous working group of IEEE PES, Western Electricity Coordinating Council, WEC, so WECC, and North American Electric Reliability Corporation, so NERC. So his research interests include renewable resource integration, power system protection, and power system modeling and simulation. So and just to let you know that Dr. Haddadi has made a lot contribution on the protection of renewable energy based power grid. So for sure today we can learn a lot from him. So with saying that one, let's get back to Abu Taleb. So Abu Taleb, floor is yours.
Yeah, thank you. Thank you, Saeed, for the invitation, and happy to be presenting here. I have met some of the students at Washington State, and at the last general meeting, I think I participated in a mentoring program, and I met one of the students. So happy to talk to you all. And the objective of the presentation today is essentially to motivate more research. You know, I don't come here with answers. It's mostly research questions. Hopefully, if you guys are interested in conducting research in this area, we can collaborate. And I expect more questions, more challenging questions from a university audience. So feel free, whatever questions you might have. No question is a bad question. Feel free to stop me whenever you feel or clarification is needed. And like I said, it's very informal, and hopefully it's going to be an interactive presentation, and hopefully at the end we'll both learn from each other. So motivation, challenges, and needs. Essentially, what we're seeing today in the power industry is a continuously increasing grid integration of inverter-based resources, IBRs, which are predominantly renewable resources, type 3 and type 4 wind turbine generators, battery energy storage, more and more today, especially in the New York State, where I'm based, the government has a very aggressive plan for substantially increasing the share of battery, and also solar PV inverters. And the challenge that this transformation, or this essentially we could call it a revolution, brings to the system is that there are impacts on the classical assumptions and classical analysis methods and the classical framework that has traditionally been used for several decades for operation, protection, and control of the power system. And essentially, these challenges need to be addressed in order to enable a future power system dominated by renewable energy resources. This is the focus of today's presentation. We will look at some of these challenges, and we will look at some of the potential solutions to these challenges, and the road ahead for research and development. The particular challenge that we're going to be looking at today is the impact of inverter-based resources on system protection. And the system protection has been designed over several decades around the assumption of a classical power system dominated by synchronous generators. And essentially, the design tools analysis methods, models, they have been all designed around that fundamental assumption. Now that synchronous generators are being increasingly retired and replaced by inverter-based resources, which exhibit different short-circuit response and fault response characteristics, there is an anticipated impact on the performance of the traditional system protection. And there are two aspects that would need to be researched to enable a future system protection which remains at least as reliable as today's system protection. Aspect one is need for more accurate short-circuit models of inverter-based resources that can be used by protection engineers and planning engineers to conduct these short-circuit type studies and design relays. That's the first aspect. And the second aspect is to use those models to analyze the performance of legacy protection schemes, such as distance protection, so on and so forth, to identify potential misoperation issues and to come up with fundamentally new protection and control schemes to guarantee reliable protection in the future. So I will be, in this talk, I will be focusing on the second aspect, the protection impacts of inverter-based resources, and we look at the response of the relays and identify potential relay misoperation under IBRs, and then based on that understanding, based on those findings, we develop fundamentally new control and protection schemes to ensure reliable protection of the future system. And when we talk about protection impacts, there's a wide range of relay schemes that may be prone to misoperation under inverter-based resources. Let me see if I can find the laser pointer. Yeah. Do you see the laser? Hopefully you can see it.
Yes, we can.
Okay. Yeah. So there's a range of protection schemes that we have studied in this research: power swing, negative sequence, directional elements, distance protection, so on and so forth. And then in each case, we identify what is the potential impact of IBR on that particular scheme, what are the causes, what is the root cause, and what can be done to address that. And also, we use experimental hardware-in-the-loop setups to validate the findings and validate the performance of the relay. So quickly, background, what is an inverter-based resource? Essentially, this is the definition that I took from the IEEE 2800 standard. It's a source of electric power that is connected to the electric grid through a power electronic interface, which exports active power from a primary energy source to the grid. There are different types of power electronic resources: type 3, 4, PV, battery energy storage, and also HVDC, which I haven't shown here. And essentially, the common feature to all of them is that there's a primary source of energy, and then there's a power electronic interface, which interfaces that primary source to the grid. In the case of type 3, essentially the power electronic interface exports typically 30% of the power, and the rest is directly exported to the grid through a stator connection. In the case of type 4, the converter exports essentially 100% of the primary energy source. And similarly, in the case of PV and battery energy storage, the converter rating is essentially on par with the rating of the primary energy source. So that's why we call these fully sized converters, and type 3 is called partially sized converter. Also, type 3 is referred to as doubly fed induction generator. And also, in terms of the control technology, the control can be divided into grid following and grid forming. But the main takeaway here is that this power electronic interface is a fundamental difference to classical synchronous generators, and this leads to a different fault response. What are these differences? Here's a summary of those differences in terms of the fault current characteristic. In terms of magnitude, the short circuit response of an inverter-based resource is typically limited to the nominal load current, 1.1 to 1.5 per unit, as opposed to the classical synchronous generator, which can produce a high magnitude short circuit current. Also, in terms of the power factor angle and phase angle of the short circuit current, in classical synchronous generators, the fault current is predominantly reactive, whereas with IBRs, the fault response or the power factor angle depends on the control, and depending on the type of resource and the control, it can have a mix of active and reactive power. So this is one main difference, essentially. Also, in terms of the signature, as opposed to this classical synchronous generator, whose fault response can be divided into subtransient, transient, and steady state periods for the sake of analysis, for IBRs, the fault response essentially exhibits an initial transient with a typical duration of 0.5 to 1 cycle, and then after that transient period, the fault response settles in a quasi-steady state. Essentially, the behavior in terms of subtransient, transient, and steady state may not be the same. And also, in this first 0.5 to 1.5 cycle, the fault response is uncontrolled, meaning it's not determined largely by the control scheme. And also, in terms of sequence components, classical synchronous generators provide a path for negative sequence current to follow, whereas with inverter-based resources, traditionally, essentially the negative sequence current injection is determined by the control scheme. And traditionally, because there was no requirement for control of negative sequence current, it was essentially a common practice for manufacturers to suppress negative sequence current, to not provide it. However, recently, as we'll see in the rest of the presentation, with some country grid codes such as Germany and also in North America, the IEEE 2800 standard now require injection of negative sequence current under unbalanced fault. So the main takeaway here is that the fault response of an inverter-based resource is first dependent on inverter control scheme, and second, it's non-universal because the control scheme of the inverter is often proprietary. It's a IP of the manufacturer. So because of this non-universal fault response, it's more challenging to model short circuit, to model IBR in short circuit domain. Sorry. So quickly regarding standardization, there has been some efforts around the world recently on standardizing the performance of inverter-based resources when they're connected to the grid. And essentially, standardization has been identified as one of the key aspects of increasing inverter-based resource integration and share in the power system. In the context of North America, there are two main standards for transmission and sub-transmission. There's the IEEE 2800 2022 standard, and at distribution level, there's 1547 2018. Also, the German grid code also applies to the transmission system. 4120 applies to the transmission system. So this is an example of an international code. And essentially, the reason we mention this requirement, the IEEE standard, is that the standard specifies a set of minimum technical requirements for a transmission and sub-transmission connected inverter-based resource, which also affects its fault response. And our research objective here is to study how those requirements specifically for fault response may impact the behavior of system protection. So we'll see examples how system protection operates with and without those requirements incorporated by IBR control. And this is a summary of those requirements. If you're interested, it's clause 7 of the IEEE 2800 standard, which provides requirements for voltage right-through. And the requirements are provided for both balanced and unbalanced faults. For balanced fault, these are the main requirements: essentially injection of reactive current, also to provide reactive current priority, meaning that the current capacity of the inverter is first provided for injection of reactive current. If there is any capacity remaining, it's provided to active current. And for unbalanced fault, there is an additional requirement for injection of negative sequence current as a function of negative sequence voltage. And also there are a number of requirements and or recommendations for performance of current limiter. Essentially, when the total current exceeds the current limit of the inverter, then the standards provides specifications, recommendations on how to limit the currents, because essentially inverter-based resources are current limited devices. So you have typically a 1.1 pu total current, and you have a positive sequence current and negative sequence current, active and reactive components of those, and you only have 1.1 pu. So there has to be some sort of current limiting mechanism which incorporates these requirements for positive and negative sequence current injection, and also reactive current priority. So these are the requirements, and we'll see how these requirements impact the performance of system protection. Starting with the first protection scheme, negative sequence quantities-based protection. These are schemes that rely on negative sequence quantities, namely negative sequence voltage and current, and or phase angle of these quantities to make a determination. It could be an overcurrent negative sequence or directional negative sequence to detect the direction of the fault. And the way so the objective here is to first research the negative sequence fault response of a power electronic based resource, an inverter based resource, and also to study the impact of that response on the performance of system protection, on the performance of negative sequence quantities based protection. And in this table, I summarize the different characteristics of the fault response, of negative sequence fault response of inverter based resource compared to a classical synchronous generator. And here you can see in phasor domain, the negative sequence fault current contribution of a classical synchronous generator compared to a traditional control for type 4 wind turbine generator, compared to a control based on IEEE 2800 standard. So as you can see here, under synchronous generator, the magnitude of negative sequence current is relatively large, and the phase angle leads the negative sequence voltage by 90 degrees. One point to emphasize here is that synchronous generators do not generate negative sequence current. Essentially, the current that is produced and sold by synchronous generator is positive sequence. However, they provide a path for negative sequence current to flow, meaning if you have an unbalanced condition in your network, if you have unbalanced voltage and negative sequence voltage at the terminal of the synchronous generator, the generator provides a path for negative sequence current to follow, and it's a low impedance path. Therefore, you get a relatively high magnitude negative sequence current. However, with type 4 wind turbine generator, which I'm showing in this example, if you do not design the control specifically to inject negative sequence current, under classical designs, the magnitude of negative sequence current is much smaller compared to synchronous generator. And also the phase angle, as you can see, it's no longer reactive. It's actually capacitive here. And when we adopt the IEEE 2800 standard, now with those requirements, and keep in mind that this is one implementation of the 2800 standard. I will not get into that this conversation, but essentially there are several ways to implement those requirements. And here we're using the K-factor approach. With this approach, the negative sequence behavior emulates that of a classical synchronous generator, of course, subject to current limits. Now we study the performance or the response, the impact of that performance on relays. There are two causes of potential misoperation that has been identified on negative sequence quantities-based protection. The low magnitude negative sequence current injection can lead to misoperation of negative sequence over current element, and the changed power factor angle could lead to misoperation of directional negative sequence element over current element. And these are examples for synchronous generator type 4 and type 4 with IEEE 2800. And here you can see the performance of negative sequence over current and negative sequence directional elements under synchronous generators. So in this case, this is a unbalanced forward fault for the relay. So for synchronous generator, the operation of the relay is successful. The overcurrent element asserts, and the directional element also declares forward direction. Under type 4, with no negative sequence current control, the overcurrent element doesn't pick up, and the directional element mistakenly declares a reverse direction. With the adoption of the 2800, now the operation is successful. So this illustrates that essentially adoption of the 2800 or similar requirements, such as the German code, can help mitigate some of the potential misoperation issues related to inverter-based resources boson system protection. Another impact is on line distance protection. And in this case, the cause of potential misoperation is the unpredictable and inconsistent dynamic expansion of the Mohs circle, which may lead to reduced reach accuracy and risk of over or under reach. Here is the mathematical demonstration of that problem or that undesired behavior with type 4 or with inverter-based resource in general. The Mohs circle can exhibit a unpredictable expansion, which is a function of the source impedance behind the relay. And when the source behind the relay is a type 4 wind turbine generator, this impedance can become unpredictable and inconsistent depending on several factors, and that could make it challenging for protection system to know beforehand the extent of this expansion and set the relay accordingly. And this is further research into factors influencing that dynamic expansion. Here we have identified the type of resource, whether it's a fully sized converter or partially sized converter, has an impact on the extent and the characteristics of that expansion. Also, the number of inverter units in service, how many wind turbines you have in service at the inception of the fault can make a difference on the extent of expansion. Also, wind speed and the polarization scheme used by the relay can have an impact. So this shows the challenge of designing a robust system protection or distance protection when you have high share of IBRs. Another impact is on power swing protection. And in this case, the identified misoperation issue is caused by an increased rate of change of swing impedance. Essentially, the power swing becomes faster under inverter-based resources, and the power swing scheme may not be able to detect such a fast power swing, and essentially mistakenly declare a power swing as a fault. The other cause is the change swing impedance trajectory and due to IBR dynamics, and this characteristic can make it challenging for the out-of-step tripping scheme of the relay to differentiate between stable and unstable swing. And the potential recommendations that we have studied here include reducing the time delay of the power swing blocking scheme to make the function more sensitive to power swings, essentially to be able to detect faster swings under inverter-based resources, and also to reduce the reach of the inner blinder of the power swing out-of-step tripping function to be able to differentiate between stable and unstable swings under inverter-based resources. And here's another research into modeling requirements for power swing studies. So traditionally, protection engineers and planning engineers, to perform power swing studies, they have relied on classical models of synchronous generators, and the models and the modeling requirements are well established for synchronous generator. The research question is, if I have a system with high share of inverter-based resources, what type of model, what are the modeling requirements for inverter-based resource? So this could be a very nice PhD, if you're looking for a topic. And what we did here to establish those requirements is we studied two candidate models. One is a detailed electromagnetic transient type of IBR, EMT type IBR model, and the other is a stability type IBR model. The difference between these two is that the EMT model uses a very detailed representation of IBR, which considers fast IBR controls and essentially as much level of detail as you wish, whereas the stability type model only represents dynamics in the typical range of stability studies, which is close to 6 years. So in terms of dynamics, it doesn't capture as much dynamics or the wideband model. However, it's more the stability type model because of its lower computational burden is more suitable for power swing studies of large scale networks. So this is the model that has traditionally been used, in traditional networks. These are the type of models that are used for power swing studies. We want to see whether the same models can be used for inverter-based resources, or do we need to now use EMT type models. So we cross-examine these two, and we observe that when the share of IBR is low, in this case 25%, these two models provide consistent result in terms of power swing characteristics, the power swing blocking, time delay, and out-of-step tripping performance of the relay. However, when we increase the share of IBRs, then we start to see discrepancies between the two models. So essentially, the conclusion here is that there's a need for improvement of existing generic IBR models under high share of IBRs. And since this research was done, there has been a new generation of stability type models that provide a more consistent result under higher share of IBRs. But this work can certainly continue with more and more improvements. Quickly on other schemes, we have studied the line current differential and the potential impacts, specifically the traditional line current differential, which is based on slope, seems to be immune to inverter-based resource fault response. So this is there's no impact, at least to the extent that we studied, on the performance of traditional line current differential, but more let's say more recent schemes, the alpha plane approach shows some misoperations, These have been documented in this report. And since we published this work, the manufacturer of Relay, which implements this approach, they came up with an improved scheme and an improved scheme and setting to make this line current differential also prone to make it immune to protection misoperation under IBR. And these are some examples of those misoperation for the alpha plane approach. For synchronous generator, of course, we didn't see a misoperation. For type 4, with no negative sequence control, we saw misoperation both for the phase line current differential and the negative sequence. And with adoption of the 2800, those misoperation issues were addressed. And for traditional slope-based LCD, of course, we didn't see a misoperation. Also, fault identification scheme can become prone to malfunction due to the changed phase angle of negative sequence current. And in this case, you can see the fault was on phase A, but when the inverter did not inject negative sequence current, the fault identification scheme mistakenly declared it in phase, sorry, the fault was on phase A and the scheme declared it on phase C. And with the adoption of 2800, the operation was successful. And also on communication assisted protection and also memory polarized zero sequence directional elements, there are impacts. And on phase comparison protection. So if you're interested to know more about this, you could refer to the references or you could contact me. And also on under frequency load shedding schemes. So this is another interesting research area if you're interested pursuing. Specifically, we found two main causes of potential misoperation. One was potential for excessive load shedding by under frequency load shedding due to the reduced system inertia and higher roll-off and deeper frequency excursion. So you can see here, this is the trace of frequency. There's a load change here or loss of generation here, and basically with classical synchronous generator, this is the a trace of frequency and UFLS level 1 and level 2 assert. However, when you have higher share of IBRs due to the reduced inertia, you see a faster roll-off and a deeper excursion of frequency, which causes level 3 to also assert. And with the additional load shedding that happens here, when the frequency returns to normal, it can exceed the allowable instantaneous over frequency trip setting of generators. So it could lead to cascaded outages of generators. So that's one cause. The other cause is when you have a distribution system which has a high share of distributed energy resources, and in this case, because of the over voltages that may happen, that may be caused by these resources, the UFLS scheme, which uses which uses under voltage inhibit threshold or inhibit element, may malfunction and lead to unwanted UFLS operation. So that's a summary of the identified misoperation issues. Here, I give a very quick overview of two case studies that we conducted on actual utility systems. The first one was for the New York State transmission system. The objective here is to study the protection system performance in an area of the New York State system within NYPA territory, which has a high concentration of wind park. This is a schematic diagram of that region. And the objective is to identify potential relay misoperations due to these wind parks and identify potential solutions to those. So here we developed a detailed electromagnetic transient type model of this region specifically, and we modeled relays and we modeled wind generator controls, and we studied potential relay misoperations. So one identified misoperation was the overcurrent element because of the lack of zero sequence current injection by wind parks because of the type of transformer configuration. So this was not strictly related to control, but mainly related to the configuration of the wind park transformer. For unbalanced faults, the elements, the relay elements, which relied on zero sequence quantities, did not properly operate because of the lack of zero sequence current. The other scheme was distance relay, and in this case, remember I talked about the dynamic expansion and the unpredictability of the expansion under inverter-based resources. So here we saw that there is a location which uses a MO element, distance relay, and because of the wind parks that are close to that location, the dynamic expansion becomes uncontrollable and unpredictable, and we saw a number of cases with overreach. And also, the memory polarized directional element also showed a case of misoperation, and the cause of that is a faster inverter-based resource control and reduced inertia, which caused a shift in the phase angle of the short circuit voltage with respect to the memory voltage, leading to an incorrect directionality decision. Another case was the National Grid UK, and in this case, again, we studied a region which has a high concentration of inverter-based resources and modeled that region in detail in an electromagnetic transient type software and included relay models as well. And here we saw that region uses line current differential, and we saw no misoperation, as I mentioned in the previous slide. The traditional slope-based element or line current differential is immune to IBR-related misoperation. This is what we saw here in the system, but the distance protection that was used showed a number of misoperations, mainly related to the low current contribution of inverter-based resources, which caused misoperation of a supervising overcurrent element in the distance relay. And also, there are potential misoperation for weak grid in-feed scenario and high resistive faults. Main takeaways. We see that with increased share of inverter-based resources, there is a risk of protection misoperation due to generally lower fault current contribution of IBRs and dynamically changing fault current phase angle and the faster IBR controls and reduced inertia. So these are the three key causes of misoperation. And by adoption of the IEEE 2800 standard, it is possible to address some of these misoperation issues. However, we need to always keep in mind that these solutions, they have their own limitations also, because at the end of the day, inverter-based resources are current limited devices. So for example, with negative sequence control, if you inject negative sequence current, then you have to, reduce the positive sequence current to make room for negative sequence. And that could lead to other impacts. Essentially, the full extent of the adoption of the standard and the impact on system protection is still unknown, especially when you have a very high penetration of inverter-based resources. And also, another emerging research area is grid-forming inverters and how they would impact, because what we talked about in this presentation and what we have been considering so far is mainly grid following technology. But Now, with the adoption of the grid forming technology, what's going to happen to system protection? That's an open question, and hopefully for your young minds, you can help address some of these challenges and make sure that the future power system has a reliable protection. So with that, thank you very much. Let me know if you have any questions.
Okay, thank you. That was excellent talk. So let's go back to questions. Maybe let's go to the online people. So anybody online has questions? You may unmute yourself and ask a question if you have. Or not? Okay, yeah, we can come back always to online people. So here, anybody has question?
I have a question.
Yeah.
So thank you for your talk. I thought it was very interesting how it was laid out for the IEEE 2800 system or recommendations. So when a lot of the results I saw were related to simulations done with the type 4 wind turbines. Are there any particular differences when trying to reflect some similar kind of things related to the like a solar farm? Are there any particular challenges related to that, or is it that IBR is IBR, and as long as you can inject the right currents, then there isn't too much of a issue?
Yeah, that's a very good question. So the short circuit response of type 4 and PV is mainly determined by the grid side converter, which is essentially the last layer of the power electronic interface close to the grid. So in terms of if these two, or if the grid side converter control of type 4 and PV are designed with the same control objectives, then the expectation is that the short circuit response of type 4 and PV become comparable, and therefore the protection impacts would also be consistent. So essentially what we have seen is that type 4 and PV exhibit by and large the same fault response, so the protection impacts are expected to be similar. Type 3, it's kind of a different different beast, because the fault current has two components, one coming from the grid side converter, which is consistent with those of type 4 and PV, but there is another short circuit current component coming from the stator. And because of that, there is a difference between the fault response of type 3 and the type 4 and PV. With battery energy storage, I know you didn't ask the question, but I think it's a good information to have. With battery energy storage, the difference is that the active power direction, or the direction of the active current, is from and to the grid. So in charging mode, the battery is absorbing power from the grid, and if the fault happens when the battery is charging, then depending on what type of control the battery energy storage is adopting during for that particular mode, the phase angle of the short circuit current could be different from PV and type 4. So even though it's a fully sized converter, even though it uses the essentially same grid side converter setup, the fault response could be different. In discharge mode, when the battery is exporting power, we have seen that the short circuit response is comparable to PV and type 4. So the protection impacts in discharging mode, we expect them to be consistent with type 4 and PV.
Thank you.
So I have another question. So you said that you had some system models in EMT domain for some case studies, right? So I wanted to know how big the models were, like in terms of number of buses, and how long was the simulation time that you were interested in, and how long did it take to simulate, or how long does it take to simulate the models?
Yeah, so again, good question. Protection studies traditionally have not been conducted in EMT domain. If you go to utility and to the protection department, the software they typically use in North America are PSScape or Aspen, and these are phasor domain models which consider snapshot of the fault response. So EMT model is not typical for protection studies. For research purposes, we want to make sure that we are not missing an important control of wind park because we're trying to study the fault response. So first we include all the control details, and then we figure out which one of them are consequential for short circuit studies and for fault response, and which ones can be disregarded. So here we are taking this approach. We are using an EMT domain model. The number of buses in this particular case for the New York State, it was 15. And the number of wind park locations are 6. And these wind parks are, as I mentioned, EMT type. So the level of details in the control model is it's high compared to a phasor domain model. In terms of the simulation burden, well, in this case, we're not running a long simulation. It's depending on what type of protection you're studying. I would say no more than a few seconds of simulation is needed. It's a short simulation in terms of simulation time, which allows using EMT type models, and it's a small scale network. So yeah, we don't have a high computational burden here in this case. It's feasible.
Thank you.
Yeah, I have a question. It's a marvelous presentation. I just want to ask that this simulation you presented on a transmission grid, that's in a strong grid. What will be the impact on the weak grid condition?
Yeah, so it's not a strong grid in all cases. There are some cases where we have weak grid, some of those studies. And when you have a weak grid, even in a classical system with synchronous generators, the protection is more challenging than a strong grid. So the protection engineers who design relays, they have to take specific precautions, and they cannot use the regular cookbook for relay setting when designing protection for a weak grid. Now, when you have inverter-based resources and you have a weak, so you have two impacts. First, integration of inverter-based resources leads to weaker grids. And if you already have a weak grid, then, the challenge is more. That's another good research area. If you have a weak grid, what are the additional challenges on system protection when you have high share of IBRs? At least one of the more immune protection functions was the line current differential. If the pickup threshold of line current differential is properly set, considering the weak in-feed, then we expect the scheme to remain immune to misoperation. And also other solutions include, for example, use of zero sequence quantities. But yeah, there's a whole literature on designing weak grid or designing protection system for weak grid.
Thank you.
I mean, I don't know if this is the best place to ask this question, but I think you mentioned something about the Rockoff and on the voltage. So in a case where like where there's a fault on a line, and we have a microgrid downstream that needs to disconnect at a fault. I think up to now, the ROCOV is still like the best protection element in most of the relays to island when there is a fault or when there is, when there's a fault. So, but in a case when there's a low import at the time of the fault, obviously the ROCOV will not have so much changes, or there might not even be any ROCOV. So, what are there alternatives to the usage of ROCOV in the industry in terms of islanding this type of microgrids when the import is extremely low?
So the question is regarding microgrid protection and ROCOV.
Yeah.
Okay. So ROCOV, the objective of ROCOV is one of the objectives is to differentiate or to detect a loss of mains. So when the connection to the upstream grid is lost, the ROCOV scheme can use the sudden drop in frequency to detect that and essentially operate in that case. With microgrids, now, are you talking about a case where the microgrid has the capability of standalone operation? Is that what you're talking about?
Yes.
So in that case, I would imagine that the operation is different. In that case, essentially, islanded operation is actually a desired operation, and the microgrid control has been designed for that particular operation. So I would assume that the operation of ROCOV or loss of main protection in that case would be different compared to the case where you have a distribution network and which could be active, but islanded operation is not permitted in that case. So the misoperation issue that I talked about relates to the second scenario. You have an active distribution network with distributed energy resources, but it's not designed for microgrid operation. And in that case, you want to be able to detect the loss of main condition and disconnect the loads as quickly as possible.
Okay. Thank you.
Yes.
Any question? Maybe because they don't ask question, I should ask that one. So when you implemented that negative sequence requirement for IEEE 2800, so did you have any recommendation on how you should determine the contribution of the negative sequence when you implemented some of those, or any comment or suggestion on that?
Yeah, very good question. And the 2800 standard is silent on the magnitude of negative sequence current injection. Doesn't the only requirement is for negative sequence current to be a function of negative sequence voltage, and that function could be just a proportional gain, which is called the K-factor approach of the German code, for example, and that's the approach that we have implemented. But that's not the only approach. So yeah, again, short answer is the 2800 standard is silent on the magnitude of negative sequence current. The phase angle is specified. We want it to be, we want the negative sequence current to be reactive. So for type 4, the recommendation is for negative sequence current to lead negative sequence voltage by 90 to 100 degrees. And for type 3, the range is 90 to 150 degrees. And also another requirement is that the incremental negative sequence reactive current shall have a magnitude which is smaller than the incremental positive sequence current. So your magnitude of negative sequence current should not exceed whatever your design is. The injected negative sequence current should not have a magnitude higher than the positive sequence current. And also, you know, there is some recommendations. These are not requirements, but the recommendation or preference is for reduction of both negative and positive sequence current when the current limit is reached. Yeah, but the standard does not tell you how to implement. This is essentially the philosophy of the standard. It doesn't get into implementation. It lets you as a manufacturer decide how best to implement that requirement, but it doesn't tell you do it this way. And the magnitude of negative sequence current is something that can be agreed upon by the transmission system owner and the IBR plant owner. So I can, as a transmission system owner, I can communicate with the plant owner to require more negative sequence current injection or less by, for example, changing the K factor gain.
Yeah, thank you. That was nice recommendation. So we have time for one more question. So who is the last lucky person to ask that question? You want?
I'll ask the question. I'll ask the question. So in your opinion, what type of protection is affected the most from this type of fault response?
Well, it depends on what protection scheme you're talking about. But generally, I think this is a point that I heard at the WPRC meeting, which is an interesting point, is that, you know, traditionally, protection engineers moved from zero sequence. Protection engineers moved from zero sequence to negative sequence, which was supposed to provide a better performance. And now that's changing. Now protection engineers are considering going back to zero sequence protection instead of negative sequence protection, considering all these challenges with fault response and negative sequence contribution of inverter-based resources. So I would say generally, you know, we hear more and more that negative zero sequence current would be a potential solution to some of these challenges.
Yeah, the second lucky guy, so you can ask. So, yeah.
All right. I mean, I see that in your simulations, most of the turbines that you use are type 3 and type 4. Is it like why didn't you also consider type 1 and 2? Is it because 3 and 4 are like the predominant types that are in the industry now? Sorry, like
yeah.
Okay.
Yeah, so that's one reason. And the other reason is that with type 1 and 2, the short circuit response is a classical machine. So, yeah, the short circuit response or analysis of the response of type 3 and 4 is more challenging, but they are also the dominant technology. So, more reason.
Okay.
Okay, thank you, Dr. Haddadi. It was excellent talk. So we learned a lot, and that was very informative. We really appreciate that. So maybe one round of applause.
Thank you.
And hopefully see you sometime soon in conferences or meeting, anything soon. So thank you.
Yeah.
Thank you. Have a great day.
Thank you all, and good to see you all. Have a good day.
Yeah, thank you. Bye.
Bye.
Bye.